welcome to my, today we're going to talk about the health binary and just go in depth into we're going to talk about the health executable format. So yeah, that's all. Sad day. This is the last presentation of the semester, I think.
Oh, true. Yes,
I don't like doing those. Those are not boring. Those are boring. I like real research. So, where am I? Blah blah blah. You guys know this. I just put that there because template. Oh, stuff. I didn't know what to put, so I don't. You guys don't care, either way. So, down to the real stuff. What is health binary? It stands for executable in the linkable format. This was introduced in the Unix System 5, so at the beginning of the Unix birth, and it was around the late 80s. We in this club, everyone should know what a health binary is. You've probably seen it or even play with it somehow. It's on the Linux systems, BSD, PlayStation 4, and Wii. And it's also being used as a container for microcontroller firmware. So yeah. And again, what is a ELF binary used for? It just doesn't just work as a executable. It's also used for shared libraries, object files, core DOMs. That part, it's not used as often, but it's mostly used for the executables, shared libraries, and object files. And yeah, memes, I had nothing. It was just going to be those words, so I put this to fill it up. But yeah, you can do it. Still cute, though. Okay, the main part. In a executable, there is two main parts or two specific words you need to know: segments and sections. The segments are really they're used during the runtime when you execute your binary, and the sessions are used during the link time. It's possible to have multiple sections and multiple segments, and they can overlap on each other. It's just the way the location of memory that the ELF binary points to, but it can be overlapping each other. I think there's an image on the next slide. But both of them represent data. So like code, text, all of that, it represents all of that. So as you can see in this image, we can have multiple segments. Oh my God, so many S's. So you can have the segments, and they point to specific memory address. Like I told you before, it's oh, this is the beginning of the file, and I want you to start the process from this point in memory. So that's there, and as you can see at the right, you can have sections overlapping on the segments. Nothing fancy there. Next slide is, so in a statically compiled binary, it's going to be something like this. The data is being put in first, points to the top of it. Next is a segment can also have can allocate X amount of memory just in case for uninitialized variables and things that might be needed in the future. So they can also just request X amount of space in memory. And lastly, is code. This is where we do our stuff. This is what you write or the main part of the program. So nothing fancy there. And in a dynamic linked binary, it kind of works the same, but it can be, because it's dynamically linked, it does not have to follow the same process as data, uninitialized code. It doesn't have to follow like this. It could be randomly. So it could be code first, then data, then other stuff. It does not have to be following the statically linked method process. I don't know what this picture was. Yep, I have no clue what that picture was. Again, late night typing. So this is the main part. What is the header. This contains the metadata of how the binary is designed. So it contains things like the magic bytes. The magic byte is like a special bytes that like says, oh, this is. It helps the OS determine what kind of I guess interpreter to execute the file. So in this case, we're going to see what the magic byte for ELF binary is, and it also talks about. It also has stuff like entry points. So this is like the entry point where it starts the process of the program. And again, there is 32 bits and 64. They're pretty much the same. There's just like specific data type that just gets changed from 16 bits to 32. We're gonna see that later. And in the health binary, in the definition, it has its own custom data types like half word, address, and offsets. But I'm gonna show you the equivalent to the CE version, which is right here. As you can see, the half words are just 16 bytes, words. And at the address and offset, this is where you can define if it's a 32 or 64 bits binary. And yeah, next we're going to just go through each one of them and try to discuss what they do or how they're relevant to an executable. The first one is the magic bytes, as I've said before. Oh my God, I messed up. This was supposed to be like an animation slide, but Okay, one second. We're going to do this manually. Okay. We're just going to move this down here and talk about it. So the first one is the magic byte. As you can see right here, it's 74454C46. If you see that at the top of the binary, that tells us it's an executable. And also the X equivalent would be, or the ask. This would be what it's going to look like if you do an X dump on the code. The next one, the 02, this is just telling us if the binary is 32 or 64. In our case, this is a 64-bit binary. The next bit, which is 01, bring this back up. This is simply tells us like where the significant if it's using the least significant bits first or the most significant bits first. This is just how, depending on how the compiler decides to do stuff. Okay, I think we fixed this one. And the next slide is, I just added in the next slide. Okay, ignore what I just, yeah. The next 01, this is always 1. This is the version number of the ELF. So just like how programs can update themselves, this has just been the standard for quite some time. Just the first version. It's pretty usable, good. So they never got to really change stuff. So 01 is that. And the next bit is just the OS version. So you can, usually it does not really matter. But by default, most binaries we have 0 set, so just none. Or system, like a generic OS. But if you really want to be fancy, you can specify. There's a list of them. You can specify what the OS is. The next one is nothing. We just go to the next part of the health binary, which is the E type, and this just tells us the type of health file it is. Remember when I said an health binary can be used as an executable, shared library, or something else that I just escaped my mind. But object file, that's what it is. So this is set in the E-type struct, and in there is this top 4 or top 5. 0 is just a no file type. Usually, I've actually never seen this before, but 0 means a zero file type. If it's set to 1, it's a relocation file type, and this is used for object files. It just specifies if there's a need for relocation during the linking stage, this will be used. And if example of that in the command line is gcc-c fo.c-0-o output file, and just fold that out. So object file by the O. The next one is the executable number 2, which is what we're used to, especially like the ls binary, pwd, pretty much all we have on a Linux system. Executable files, we pretty much know what it is, and we can just compile that by doing gcc-no pi fo.c.out and whatever you want it to be. And the third one is the shared library, also known as a dynamic object file. And we know this for rootkits and all that stuff. So like the LD preload, it's an shared object file. And yeah, pretty much that's it. And the last one is a core file. Again, I've not seen this being used, so I cannot go in detail with that. The next part is the machine and the version. The machine just tells us like the architecture, that word. And this is the 5 that they have, x86, MIPS, ARM, and all that stuff. And again, the version is just the version of ELF, which is always set to 1. Next is the entry point, something called the PHOFF and SHOFF. The entry point is just, again, it points to a memory address to tell where the process starts executing. The next one is the PF-off, which it points to the program header table. We're going to talk about what that looks like. And the SH-off, it points to the start of the section header table. In the binary, these are offsets. So rather than just giving the exact location in memory, it's an offset from the beginning of the file. So like, let's say the beginning is 0000000FF. The offset can be 00000 plus 8 or something. I don't know binaries that much. So the rest of the struct. So the E flag again specify this is OS dependent. So this is like how it executes stuff. I again don't know a lot about these flags, but flags are there. Not always useful for us. The EHSIE contains the size of the header, which is kind of redundant, I think, because we get to know that from the top of the header. The next one contains the size of the header, the program table. And again, I don't think I have to read all of this. They pretty much just, the last few attributes just tells you the size and the location and number of entry of the ELF binary. And if you want to try this yourself and see what it looks like, you can always use the read ELF binary itself. It's a thing on Linux. I've seen it on macOS too. You can just do read ELF-H and the location of your binary. So if you want to do ls, you can do /bin/ls, and it's going to give you all of the headers, the ELF header of that binary. Next is the program header. So again, this tells us how to create, or tells the system how to create a process image. And this is what the struct looks like. This is the 32 bits version. In the 64, it's really similar, except that the flag and I think the offsets just switch position. Reason, I don't know yet. I've been trying to look that up, but it's hard to really see why they did that. But again, they're really similar. So the beginning, which is the word type, it tells us what type of program header it is. So just like how we have equivalent in the ELF header, there's also different types of program headers. 0 is usually like a placeholder. It's just nothing. The first one is PT load, and this is the part, the segment that gets loaded into memory. And this part can be this is what is used to create like a X amount of space in memory just to allocate. This is what is used. It's used to allocate memory for other purposes. Number two is a dynamic, and it contains information about dynamic linked binaries, the things you need outside of your stuff. Interpreter is again used by the dynamically linked executable, and the rest is note. I wasn't sure what this does. I looked it up, made zero sense to me. This is the shared library. It should not be used. It's just never used anymore. And the rest, you don't need to know all of that. This is all just for the system. So the offsets, again, these offsets are just pretty straightforward, just by their names. It tells us where in the health file, where the content of the segment is located. So pretty straightforward. So the segment, that's where the code will be, points to that. And next to that is the V, is the PV address and the P address. Again, the V is just a virtual address to the segment in memory, and the P is for the physical memory address. Next is the file SZ, which is size in bytes for the segment. And the MZ, the next one, which is mem, SZ, it's just the size of the segment in memory. So just same thing, just one is in memory and the other is in the file image. The flag, this is a really important part. This is where we can specify what kind of permissions you can have in that segment. So you can have a segment where it's executable, or you can have it writable or readable. And this, obviously, you can mix this together. You can have executable and readable, or you can have writable and executable, which is always the dangerous combination. Our code usually has the flag of executable and readable, so you can read your code and execute it. And the last part, alignment, just specify if alignment is needed. I have no clue what that meant, and I had no time to really look into that, so it's not, we don't need to, if we don't need to know that, we can just put that on the table. And again, if you want to see the segments of a binary, you can always just do the read elf -- segment and your binary. And this is, where's Philip? That's for you. This is offset and the baby. And I was reading I was just writing a lot of offsets, and I was like, offset, that's a person's name or rapper's name. Then I was like, does he have any relations with the baby? And this is what came up. Just this picture with Philip's head in it. Yep, I did.
What's Photoshop?
I didn't use Photoshop. Okay, next we have the section header, and this is what it looks like. And we're gonna go through it again. There's a lot. Okay, the S name is okay. I'm gonna move back a little bit so I can help you guys understand this next part. So back. Right here. So this last one, this SH stir NDX, this is like a, how would I describe this? It contains like an index of the section header that contains the section name. So it's useful, like when in the section header it points to this location to find like a specific name. I don't know what that means, but it just points whenever the section header needs something, it points to this part to find the name of that section and does whatever it needs to do after that. So I'm just gonna go back again. Oh, okay. Yeah, like I said, it points to the offset to the string in the elf header table. The next one, again, type. There's always different types. These are the types, some of the types of section headers, and some of what they mean is the proc bit. The first, the one, is just information about the program data. The next one is information about the symbol table, and the third one is string table, and the last one, the hash one. This one just gives information about the system hash table. All of this is more of like informational rather than like help doing something to the system. And those are the rest of the attributes. There's the flag, which tells the system that, hey, this section is writable, or this section is loaded into memory, or this part contains executable code. So I think if you really want to do some fancy stuff, you can always put stuff in sections where they execute code rather than writing the code in the code section of the half binary. Yeah, most of this, again, all of this are just more of information for the OS to like point to like informational stuff for the binary to run successfully, like the size of entries, size of the section header, how many entries they have, the size of the section of itself in the file system and in memory, so stuff like that. And again, lastly, if you want to run this, you can, again, the read health binary is the lifesaver. That and dash dash section and the binary name. And I think, so all of this came from this first link. It's a YouTube video by someone named Stack Smashin. Pretty good guy. Really, really, I think explains this much better than I did. So if you want to know more about this, you can go there. Or if you want to read code like a maniac, you can always read the Linux source code and try to understand this. Yeah. Yeah, like if you want to, you can always read this, modified, have fun. That's all up to you. Why would you do that? I don't know if you have life. But if you just want to read stuff, there's this document by the people who made it, I believe. And it gives you all the information you need. It's the book 1 about the health binary. So pretty much all I just said, but like much better and something you can understand. And if you care about this, it just tells you everything about it. So far, I'm in page 1 to 5. I've not gotten really far in this book. It's a lot. It's a lot, man. But it is fun. It's like you want to stop, but it's like you get to like a cliffhanger, and it's like, but I have class, so I'm just going to. Yeah. See, it has much better explanation of what I've just said. And yeah. And I think, well, before I finish, is there any question? Please don't have questions. Because I would not be able to answer this. But if you have questions, please tell me, or meet me after the club.
My elf binaries run on Windows?
No. Well, I think I'm not even going to attempt to answer that question. What about the, one second, WSL, that Windows?
That does work.
It does work, so Linux binaries would now run directly on Windows, but if you use the WSL, whatever the name is, you can do some magic and it's going to run. I don't, yeah.
You like the movie Elf?
No. Okay, it's going to be worse if I ask you what is that movie. I don't know what that is.
You said no, you haven't even seen it?
Yeah, I think that's always the safe answer.
That's even worse.
Are we going to look it up?
You're not a good movie. That's not
But ignore everything just happened. But thank you for listening. This would be probably the last time you hear from me. It's not like I'm dying, but if I do die, this is the last time. So I'm I'm gonna leave in a peace note. I'll see you next year. Good night. I know, right? I was like, oh, I'm done. This is the last one.
He's done so much.
Time was so fast.